Hello and welcome to the second section of the Vacuum Basics NanoLab workshop. I am Ryan Rivers. I am a PVD and etch engineer here at the NanoLab. We're going to be discussing here part 2, vacuum metrology, which is the second part of the vacuum class. If you haven't taken the first part of vacuum class, I encourage you to close this video and go to part 1, which is just above it in the equipment manual. In vacuum metrology, we're going to discuss how gauges work. We're going to talk about energy transfer devices and mechanical force devices. We're going to talk about checking vacuum integrity, including when and how problem reports should be made versus you fixing your own issues. The primary goal here is to explain the rate of rise test and to also discuss leaking versus off-gassing and when to expect those to happen. There are two basic types of gauge mechanisms. There are energy transfer gauges and there are mechanical force measurement gauges. The energy transfer devices are basically light bulbs, and mechanical force measurement devices are basically balloons. Energy transfer devices operate on an energized filament which sends energy via the pressure in the cavity to the sensor filament, which is typically at a lower energy state. The pressure changes the amount of charge carriers or energy carriers in the system, which allows the energized filament to transfer energy at a higher rate the higher the pressure is. These measurements can be, the measurement of energy transfer can be back calculated to the pressure, and that can lead us to have a very high accuracy gauge in many different flow ranges, with the different energy transfer devices being built to handle various different scenarios. Typically, we pair a convectron energy transfer device and an ion gauge energy transfer device for most of our PVD systems. However, for etch and sputter, we actually use a slightly different device, which is more of a mechanical force device. The nice thing about ion gauges and various energy transfer devices is they're very accurate. The problem we run into with these gauges is that they're often sensitive to fluorine, chlorine, and oxygen plasma. That means that the etchers and the sputterers that we use during reactive deposition or reactive etch, also the PECVD chambers we use, typically cannot use these gauges easily during the process. They operate in a pressure regime that's not ideal for us given the content of the gases and can cause them to burn out quite quickly. For those processes, we typically move to a mechanical force device known as a capacitance manometer or a barotron, which is the trade name for it. Now, why don't we use barotrons for everything? Well, primarily because they're a little bit sensitive. They're sensitive to movement. They're typically limited to pressures above the 4 scale of torr. Anything below 1 to the minus 4 doesn't put out enough pressure to operate a capacitance manometer very well. There are specific designs that are better at it than others, but they are kind of expensive. The other problem you run into is they're sensitive to movement. They tend to change their behavior based on what orientation they're in. So you have to calibrate them in place in a lot of cases, or at least re-zero them. However, the benefit is they're extremely robust to almost every form of reactive gas, and they tend to be something that'll hold up for quite a while as long as you don't make actual contact with them. It's important when operating tools with a capacitance manometer not to make contact with it. Try not to knock a barotron around. It's a little can, looks like that on the picture, maybe has a different name. Barotron was the MKS variant of this, but there are many capacitance manometers out there. If you see something about that size on a vacuum system, please don't knock it around. It will come out of calibration and your process will shift. So, why do we have so many different types of gauges? Well, because we have a lot of different types of pressure. It turns out in turbulent flow and in the transitional flow region, a convectron is a very solid gauge to use, and it measures all the way up to atmosphere and all the way down to about 100 millitorr, maybe even a little less than that. But it's really hard to get data on anything below 10 millitorr with a convectron gauge. In that zone, it's actually easier for a barotron to pick up, and the barotron is pretty good up to about a torr, typically at most, but it can go all the way down to millitorr level readouts with fractions of a millitorr accuracy. The difficulty is that if you go much below that, down at 1/10 of a millitorr, it stops really being all that accurate in the first place at all. At that point, we kind of need to move on to something like an ion gauge, some kind of energy counting device that is typically a bare filament so that it's sensitive enough, but it's also very, very sensitive to being exposed to turbulent flow, and especially air. Air has oxygen in it. Ion gauge filaments are made of tungsten. They are quite literally tungsten filament light bulbs that have a sensor in them. They're just very advanced ones. And what happens if you get too much air in a light bulb? Say if you broke the vacuum cavity of a light bulb in your home, those of us who remember back before we all were working with LED light bulbs, we know that that light bulb would burn out immediately. And the same thing will happen to an ion gauge. Please don't run an ion gauge when the pressure is above 1 millitorr. If it's above 1 millitorr, you're likely to damage the gauge. Don't run the degas function of the ion gauge either without talking to staff. Let's talk about gauge placement. There are various gauge placements for processing. Typically, we have a barytron or a convectron on the chamber somewhere because we're going to need some kind of data for atmospheric behavior. We almost always have a convectron. We usually have a barytron for anything that operates in the millitorr range during its process. We almost always have an ion gauge on any high vacuum chamber. The ion gauge is typically right above the gate valve of a high vacuum chamber, and the second ion gauge is right below it. And the idea is you can compare these two numbers when the valving opens up. It not only tells you when it's safe to open that valve by checking the two different gauges, but it also tells you whether or not you have a leak in certain areas, and we can do leak testing to figure this out. Ion gauge 1 should always be higher than ion gauge 2 in this configuration. Sometimes these are wired slightly differently, and so it's important to know which of the gauges is the cryopump gauge or the turbopump gauge, and which of the gauges is the chamber gauge. If your chamber gauge runs higher than your pump gauge, that's normal. If your pump gauge runs higher than your chamber gauge, that doesn't make any sense because your pump is where the lowest pressure should be. If that's the case, your gauge is probably out of calibration. At the very minimum, we should check it. So let's talk about leaks for a second. On the subject of troubleshooting, the most common problem that I get in vacuum has always been, help, it won't pump down. There are a series of steps that you can take to solve this issue. First off, you can identify your pressure regime and then apply one of these scenarios. So if you're in the turbulent flow regime, as in you have not gotten below 100 millitorr yet, you should just vent the tool, wipe the seal down, and pump it back down. Because if you're stuck at 100 millitorr, something is wrong with your seal. If you're in the crossover region, as in like you're just at or below 100 millitorr, or you're down to about 10 millitorr, but something's going wrong with your pump, and you're still not getting a pump crossover, you should check your gauges, and you should report any problems that you're incurring on a yellow fault. The reason I say report the problem is if the system does not see that you have crossed over, you are ready to cross over and engage the crossover, that could be a logic circuit or a loose wire, and I would want an equipment engineer or myself to come take a look at it. However, if it's just been about a minute, always give a vacuum system about 10 minutes because it might just be pumping a little slower. If we had somebody put tin or indium down prior, they're going to be a little slower in the pump out, and so you sometimes just need a little bit of patience. But if you've been waiting 10 minutes past your crossover time period, something is wrong and you should talk to us. Now, once you've crossed over into a high vacuum situation, then often what people will say is it's at 5/6 and it won't pump down. That comes from a bit of an unrealistic expectation. The fall from 1 to the 3 to 1 to the 5 or 1 to the 6 is very quick. And the continued drop after that asymptotes out, as you can see, quite a bit. And eventually it's just going to stop moving. So if the pressure is steady for 15 minutes, then you have a problem if you're not at your base pressure, and then you should report a fault. But if the pressure is actively dropping over the course of that 15 minutes, just give it some more time. You'll be able to get something done well before I arrive, and you probably would be able to start. Now let's say that you were going to report a problem. What I would like you to do when you're going to report a vacuum integrity problem, what I would like you to do is seal the chamber and do what's called a leak test. The first step of that is to close all of the pumps and inlet valves for the gases. Make sure all of those valves are closed. Mark the initial pressure down at that's time equals 0. Then every 30 seconds, you're going to mark the pressure of that 30-second timestamp in the main chamber, and you're going to let it leak up slowly. Now you're going to plot that pressure on a graph, and these are going to be linear axes, not logarithmic like earlier. We're just simply trying to see what's going on. So if you have a straight line and it's just going up, that's a chamber leak, and you should report a yellow fault. There's a chamber leak in the system. If you're following the yellow line, you're typically seeing the off-gassing of some kind of material. So why is that yellow line the curvature it is? Well, off-gassing is a stable vapor pressure that it will come to, and eventually your chamber will come to that pressure. Now, sometimes you can have something with a very high vapor pressure and a lot of source, and it's never going to come down that fast. And it might look like a leak to you, but eventually it will taper off. The answer to a chamber leak has to be a staff member intervention, except for wiping the seal down. The answer to off-gassing is to just keep pumping for a little while longer. So let's say you have a chamber leak and or an off-gassing scenario. What can you do? First off, you can open the chamber up, vent it up, wipe the door seal, and that should help with that atmospheric leak you see up there in the corner. The second thing you can do is make sure you never have any skin contact the machine, or if you do, wipe it off before you close out the system. The third thing you can do is to have a very clean substrate. We have had some dirty substrates over the years, and those take 2 to 3 times as much time to pump down. And that's vacuum metrology. So the questions you should ask yourself and be able to answer are, what are the 2 major categories of gauges? What pressure regimes do they operate in? How do you tell if a gauge is out of calibration? Specifically the ion gauge example, and whether or not one's in the chamber versus one's in the cryopump. You should know how to perform a rate of rise test. You should know what kinds of problems can prevent reaching base pressure. And you should know what kinds of problems require staff intervention to move forward on. This is the end of the vacuum class. You can now take the vacuum class online technology test through the Mercury Web interface, though you will need to do so at the front desk. We only allow testing from the front consoles in the NanoLab office itself. If you need to take evaporation class or etch class, those can be found on Chapter 6 and Chapter 7 of the manual respectively. They are available online, and you can take those classes before taking this technology test. However, until you pass both the vacuum class and the evaporator class or etch class, as is appropriate for the tools you are trying to train on, you will be unable to qualify on that equipment. So I suggest you try to get those out of the way as quickly as possible. Hopefully this has been informative. If you have any questions about what you have seen here or the content inside of this class, please feel free to email me at rrivers@berkeley.edu. I will happily answer any questions that you have about the material. Thank you for your attention, and hopefully you understand high vacuum a little bit better than you did before.